and thank you for joining us today. I'm Kristen Norton, the OpticStudio Product Manager at Zemax. It's my pleasure to introduce part 2 of our two-part joint webinar series with Lumerical. Today we'll be discussing the interoperability between Zemax's software and Lumerical software and how this can be used to simulate optical systems with metalenses. So to get started, let me introduce our presenters. Akhil Bhagat will be presenting the slides for Zemax. Akhil is an optical engineer here at Zemax, and he works on the OpticStudio engineering services team. We're also here with Amy Liu, and she's the product manager at Lumerical. Amy will be presenting the Lumerical slides, and she'll be talking more about the capabilities of Lumerical software. We're also here with Dr. Reza Khorasaninejad from the Federico Capasso lab at Harvard University. Reza will be discussing ultra-thin optical components, or metasurfaces, for high-performance wearable optical devices. Akhil, Amy, and Reza will be available for a live Q&A session at the end of this webinar, and you are more than welcome to submit questions at any time throughout this webinar using the questions section of the GoToWebinar control panel. So with that, I will hand it over to Akhil.
Thank you, Kristen. So some overview on Zemax. Zemax delivers software, training, and support services for optical, laser, illumination, and optomechanical system design. We've been developing and supporting optical and illumination software for over 25 years, starting in 1990 when Dr. Ken Moore founded the Zemax Development Corporation to commercialize Zemax optical design software, which we now call OpticStudio. The initial versions of our software were aimed at classical lens design, but over the years the capability and breadth of systems it could handle has expanded immensely. We have headquartered in Seattle, Washington. However, we have global offices in the UK, China, Japan, and Taiwan. Zemax has a virtual prototype product suite of OpticStudio, lens mechanics, as well as hands-on training on both of those softwares. OpticStudio, as I discussed, is an optical system design software. Lens mechanics is an optomechanical packaging and analysis software.
So this is Amy from Lumerical Solutions. We're based in Vancouver, Canada. Our company was started in 2003 and is led by 4 photonic designers. And today our products are licensed by some of the world's most innovative organizations in more than 40 countries. That includes 800 plus customer sites, 10 of the 15 largest technology firms, and 46 of the top 50 engineering and technology research universities. And here's a list of our products. For optical simulations, we have FDTD solutions and mode solutions. And these products contain the optical solvers that can be used with OpticStudio. And today we'll be focusing mostly on FDTD solutions. We also have device for electrical and thermal simulations, as well as interconnect for circuit or system level simulations of photonic integrated circuits.
Modern optical devices often incorporate both nanoscale and macroscopic optical systems, which brings about the need to accurately model a single optical path as it traverses through different regimes. In order to combat this problem, Zemax and Lumerical have collaborated to allow a seamless transition between Lumerical's solutions and OpticStudio's ray and wave-based solutions.
So as Gil mentioned, no single solver can accurately or efficiently capture optical effects at both nanoscale and macroscale, since they tend to require different types of physics. Nanoscale optics require simulations of electromagnetic fields, and this is what all of Lumerical's photonic solvers do. And very often these solvers will carry out direct simulations of Maxwell's equations. And these simulations tend to have very few approximations, which makes them very accurate and really ideal for cases where you need to capture light interaction with wavelength scale or sub-wavelength scale features. However, they also tend to be very time-consuming and memory-intensive, which makes them not very practical for optically large geometries. So on the other side, we have macroscopic optics, and these are based mainly on the ray or wave approximation models of light, and both of these options are available in OpticStudio. The ray model is accurate for systems where any optically relevant components are much larger than the wavelength, and the wave model approximation is accurate for relatively simple geometries on the scale of wavelength, but it does start to break down with more complicated structures. So OLED and LED display is a good example of an application where both nanoscale and macroscale optics are required. here you would want to use ray tracing methods to design your macroscopic device. So in this case, on the right side, you see a lamp with dimensions 20 millimeters by 30 millimeters. So if you zoom into one of the pixels, you'll see that these devices often have very thin layers, which can be tens or hundreds of nanometers in thickness. And sometimes you may even have nanoscale structures like the photonic crystal patterning that you see here. And these dielectric rods are placed about a few hundred nanometers apart. So in order to capture the effect of light interaction with these nanoscale features, you will need to use a solver that's based on nanoscale optics. So let's look at Lumerical's optical solvers for nanoscale optics. Lumerical provides a wide variety of electromagnetic field solvers to address nanophotonic applications with different length scales. Even at the nanoscale level, there's really no single solver that's going to be ideal for all types of problems, and often multiple solvers are required to get the most efficient workflow. So first we have the stack optical solver. This is based on analytical methods, and it's meant for multi-layer stack analysis. For solvers that are based on direct simulations of Maxwell's equations, we have the eigenmode solver, which allows you to analyze the eigenmodes of a waveguide or fiber with arbitrary cross-section. For light propagation in large guided devices, we have the 2.5D variational FDTD solver, as well as the eigenmode expansion solver. And finally, for light propagation in truly arbitrary 3D geometries, we have the finite difference time domain solver. And the FDTD solver is what we'll be using today to do our diffractive or metalens design.
On the OpticStudio side, we have three modes: sequential mode for classical optical design, physical optics propagation, which is a tool within sequential mode for laser and fiber systems, and non-sequential mode for illumination, lighting, and stray light. Sequential mode is often used for designing imaging systems, afocal systems, and other sequential systems. Physical optics propagation is often used for lasers and fiber coupling, and non-sequential mode is often used for illumination, real sources, stray light analysis, optomechanical design, and other non-sequential designs. Historically, there has been many challenges converting light from nanoscale to macroscale optics when it comes to simulation. Some of the challenges included were the need to exchange data between electromagnetic field solvers and Rayer waves. It's a manual conversion which can lead to human error, and it wasn't always intuitive. Because of this, Zemax and Lumerical are collaborating with the goal of providing end users a simple workflow for a wide variety of applications that involve both nano and macroscopic optics.
So currently there are a number of ways to exchange information between Zemax and Lumerical's optical solvers, and these are available in Lumerical's optical solvers from our most recent release in June. And this you can download from a website, and it's also compatible with OpticStudio version 16 and beyond. So the first type of interoperability is that the EM field information can now be exchanged using the Zemax beam file or the ZBF file format. And this is relevant for most applications. And it includes a set of script commands, the ZBF import and export, which you can use if you want to store the field in one software and use it in another as a source. The ZBF read and write for loading and saving field data into your current workspace. And there's also a UI component that you can use to carry out the same functionalities without using the script. So for some applications, the direct exchange of EM field information doesn't make a lot of sense. So for example, for the OLED and LED display applications that we went over before, you would actually need to convert the field information into a ray set first before importing it into OpticStudio using a source file object. And for now, this does require some additional scripting. And the same goes for other formats. For example, if you want to simulate a rough surface with an EM solver and extract the BSDF function from it, you'll also need to do a bit of post-processing to get the data in a format that can be read by OpticStudio. And we're very happy to provide some sample scripts to help you do this. And depending on the type of feedback we get from end users, we would certainly like to build this directly into our products in the near future, so you don't have to do this additional step. So in last week's webinar, we went over a few application examples to demonstrate the different ways you can exchange data. between OpticStudio and Lumerical. So we went over lens to fiber and waveguide coupling, OLED and LED display, a little bit on BSDF function, and we also had a preview for the diffractive metalens design. So today we're going to be taking a deeper dive into the diffractive and metalens application for wearable optics. And as Kristen mentioned, we're very happy to have a guest speaker who is one of the leading experts on the subject today. Lens design is really all about having precise control over the phase, amplitude, and polarization of light. Traditionally, this is done a lot through lenses based on refractive optics, which requires very bulky lens systems and really doesn't work well for wearable applications since there's very little potential for miniaturization. With diffractive optics, miniaturization is much easier, and these are based on interference and diffraction principles, and they allow for much thinner elements like the Fresnel lens that you see on the right side. Fresnel lenses are very popular among today's virtual reality and augmented reality applications. So metalenses take this one step further and uses metamaterials or metasurfaces to give you almost arbitrary control over the phase, amplitude, and polarization of light. The idea here is to create an effective macroscopic behavior through artificial unicells or atoms constructed with wavelength scale features or sub-wavelength scale features. So you can see in the image on the right side, this is one unit cell of a metamaterial. And all of the features you see here are sub-wavelength scale. And users can essentially design the unicell based on the EM response they want for the lens and achieve optical properties that are really not possible with conventional optics. As I mentioned before, our guest speaker, Dr. Khorasaninejad, is one of the leading researchers in using metalenses for wearable optic applications. And for these applications, both EM simulations and ray tracing are required since the metalenses contain sub-wavelength scale features, as you can see on the left image here. And while the lens systems still need to be optimized using ray optics, like OpticStudio. So here, Lumerical's FDTD, or finite difference time domain solver, can be used to simulate light propagation through the metalenses themselves, and that will include all the effects of these sub-wavelength scale features. OpticStudio's physical optics propagation tool can be used to propagate an arbitrary beam and optimize a lens system based upon analysis of the beam's propagation. And the methodology we'll demonstrate today start with using FDTD solutions to determine the phase of the light and how it changes based on certain design parameters. And using this information, we can come up with an initial design for the lens and run 3D full FDTD simulations. After this, we can export the near-field result into a ZBF file for OpticStudio and use OpticStudio to propagate this beam into an optical system. So now Akil and I will take you through a very simple example to demonstrate the steps that I just went over. And the same methodology can be applied to both diffractive lens and metal lens design. The only real difference is the size and the geometry of the unit cells. So for this example, I'm going to set the wavelength to be at 0.532 microns. And I want to design a lens with a focal length of 3 centimeters at this wavelength. And for the lens geometry, I'm going to use diffraction gratings. And I'm going to fix the height at 1.5 microns, the pitch at 1 micron. And I'm going to vary the duty cycle to achieve the desired phase for the focal length that I want. And for real lens design, you'll likely have many more parameters to play with, but the methodology is essentially the same. So first step here is to determine the target phase profile that I need to achieve the desired lens properties that I want. And here I'm just going to use a very simple hyperboloid phase profile, and it's drawn here. And this is going to give me a focusing lens. And for much more complicated lenses like the ones that Reza will be talking about today, you may want to use OpticStudio to determine the target phase profile instead of just using a simple function like what I'm doing here. So once we have the target phase profile, we need to come up with the initial design that's going to give us this target phase profile. So to do this, we need to know how the phase of light varies as I change the duty cycle across lens. And this can be done very easily in FDTD solutions, and I'll demonstrate that now. This is FDTD solutions CAD. So to determine how the phase of the light varies as I change the duty cycle of the grating, I'm going to start with an infinitely periodic grating. So here my simulation region is the orange box, and it has a width of 1 micron, which is the pitch. The simulation boundaries in the two sides have been set to periodic. So the simulation will be as if I'm repeating this unit cell infinitely in both directions. So it's infinitely periodic, and this is just one of the unit cells. And I'm going to use a plane wave source launching from the bottom substrate. And there's a monitor here in yellow that sits right on top of the grating so that I can use to measure the phase. And I have a script here, a very simple script, which is going to sweep the duty cycle and plot the phase as a result. So each simulation takes a few seconds, and you can see the duty cycle is being changed and a separate simulation is launched. And once this is done, you get a plot of the duty cycle versus phase. So coming back to the slide here, this is the same plot as before. So this is a duty cycle versus phase. And here I'm also showing the field profile for the duty cycle of 0.05 and 0.6 on the right side. And you can see how different the profile is, and you get a huge phase difference between the two. So the FDTD method really allows you to capture all of this information. Now, using the target phase profile from before, as well as the map of the duty cycle versus phase that I just generated, I can now come up with an initial design for my lens. So basically, all I have to do is to take this target phase profile and read off the value of the duty cycle that is required to give me the phase I need for a specific location. And I also have a very simple script for doing this, and it generates the duty cycle versus position across the lens, as well as creates the lens itself. So I'll come back to FDTD here to show you what this looks like. So this is now a simulation of the full lens. This is about, I think, 400, so 200 micron in radius, so 400 micron in the entire width. And I'm just going to run this in 2D for now, since it's much quicker. And here you can see that the initial estimate is about 2 minutes, but the light actually propagates through this lens very quickly, and the simulation will auto-shut up very quickly. And my simulation here is no longer periodic. I'm actually simulating a finite lens size of a radius of 200 microns. Okay, once this auto shuts off, in the same directly, you should see a movie. So once the simulation finishes running, you can open the MPEG file that's generated from the simulation. So this just shows you how the light propagates through this lens as a function of time. You can see the source, the phase of the light changing as the duty cycle changes. And this changes basically how fast light propagates across the lens, and you get a focusing behavior. And coming back to the project file, you can see that there's a monitor. From the monitor that's placed on top of the lens here, you can right-click and visualize the field. So to export this field, so this is in 2D for now, but to export this field, all you have to do is type ZBF export and the name of the monitor, which is field, and then it's going to give you a prompt here, and you can save this field information into a Zemax beam file, which Akil can then use for his OpticStudio simulation. So before handing things off to Akil, I just want to mention that the ZBF export function only works for 3D Lumerical simulations for now. The 2D simulation is a nice proof of concept for the sort of the initial stages of the optimization. But at some point, 3D simulations will be necessary. And I did run this lens simulation in 3D. So this is the same lens as before. And this is a project file that you can see here. And for example, if you zoom in, you can see the grooves for the different gratings. So for a lens of a radius 200 microns, my total simulation region size was about 420 by 420 by 2 microns. And this simulation takes about an hour to mesh in FDTD and about an hour to run on my desktop. So even these really reasonably large size lenses can be simulated in a reasonable amount of time in 3D. And once this is done, I can take the same monitor. So again, this monitor sits just on top of the lens here. I can right-click and visualize the electric field. And you can see this is the near field result that I'm using the ZBF export function to, and I can save this into a ZBF file for Akil. So now I'll hand things off to Akil to show you what to do with this file in OpticStudio.
Thank you, Amy. So yeah, after Lumerical creates the beam file, we're then able to import that beam file into OpticStudio. Here I have a very simple system in which I'm just propagating the diffractive beam 35 millimeters or 3.5 centimeters. And if you remember, Amy said that the beam should be focusing at 30 millimeters or 3 centimeters. So to import the beam, what we can do is using our physical optics propagation tool, which is under our Analyze, Physical Optics. It'll open the Physical Optics Propagation, and then inside of the settings, we can go to Beam Definition, and we can choose a beam file here. The beam file that Lumerical created was metalens, radius 200 microns, .cbf. I've imported that here, and I've already loaded it. And by loading it to 35 millimeters, we get this beam profile. Of course, 35 millimeters is slightly beyond the focus, so we can also look at the beam profile at every single surface. And you can see that here in our shaded model, where we see the input beam with a circular aperture around it, also seen here on the right side of the screen. And we propagate it 10 millimeters, then 20 millimeters, then 25, 30, and 35. As you can see, it gets into focus, and then it starts going out of focus around 35. And we can also look more closely at the beam at 30 millimeters here in Beam File Viewer 2, where you can see the focused beam. Once we have the beam in OpticStudio, you could add any surface or any lens system as usual, and then optimize for different properties of that beam, depending on what your use case is. To summarize what we've done, we used FDTD solutions to determine the phase dependence on design parameters. We did a full lens simulation in FDTD solutions for verification. We then exported that file into OpticStudio, and we propagated the diffractive beam in OpticStudio using the physical optics propagation tool.
And now we're very happy to introduce Dr. Khorasaninejad. He's going to be talking about flat lenses, metalenses for multifunctional photonic components. Dr. Khorasaninejad is from Federico Capasso's lab at Harvard University, and here's some information on his research. And now I'll pass it off to him to give you the rest of the presentation.
Thank you very much for introduction, and thank you for inviting me. So my name is Reza Khorasaninejad, and today I would like to talk about the flat lenses, multifunctional photonic component. Here is the outline of the talk. So the talk would be about the metasurface-based lenses. So we call it flat lenses or metalenses. First, I will show how we can make an ultra-thin lenses that can focus the light down to the diffraction limit. How this singlet metal lens can resolve subwavelength image. And at the end, I will show how can we make multifunctional metasurface lenses, or specifically here, multispectral chiral lenses. So first, let us start why we are interested in this technology. If we look at the emerging technology like wearable optics or portable optics, they require components with low form factor, and at the same time they need a low cost and enhanced functionality. So that cannot be achieved using a refractive or diffractive optics, conventional optics. The problem with the refractive optics is they are heavy and they are costly. Problem with the diffractive optics, or some issue that diffractive optics need to be solved, is they cannot be integrated. For example, look at the grating or thin film deposition. If they need a certain substrate, and vertical integration is not that easy. So if you want to make a complex system or complex optical component, it will become large and costly. Some of the example is like a objective, microscope objective, or photographic camera lenses. So the idea here is whether we can use these metasurfaces because they are flat and they are ultra thin, cascade them to make complex optical system, still keep the low form factor small, and reduce the cost. That's the goal. So what's the concept behind the metasurface? Specifically in our case, we are interested in dielectric metasurfaces. So we have a building block, or I would call it a phase shifter, because most of the components that we are designing are phase plate, like a lens. You just need to control the phase of incident light and have the maximum transmission. So in our case, we using a dielectric waveguide. So it's a titanium dioxide nanopillar on top of a glass substrate. You can see it as a truncated waveguide. So we have a waveguide. We can control the effective index of the waveguide by controlling the diameters. So here we show by FDTD from Lumerical, if you change the diameter from 100 nanometer to 220 nanometer, the phase due to the propagation along the length of this nanopillar, which is 600 nanometer at wavelengths of 532, the phase can change from 0 to 2 pi. That's all you need to control the phase profile of an incident light and shape it to arbitrary shape that you are interested. So you will find out your phase profile that is required for a lens or for a hologram, for whatever you design. Then at each position, you have a phase library is this. You need the phase, you put the structure with the certain diameter or certain size that you want. Then if the incident light come, at each position, you control the phase and you shape the light at the output. What's the benefit of this platform and technology? So it's a straightforward fabrication. Generally speaking, they just need one mask level, which reduce the cost. They are compact. In our case, it's 600 nanometer tall at most. So they are lightweight and they are compatible with vertical integration. You can vertically integrate them to make a complex optical component. The reason is after you fabricate the first, you can encapsulate it, planarize it, and fabricate the second layer. And one of the most important aspect and feature of metasurfaces is they can overcome some of the limitation or issue the conventional optics has. So we are interested in visible range. So we are using titanium dioxide. We start with the substrate. Here is a glass. Sorry. Here start the substrate. Here is the glass. Because we want to be transparent at the visible range, you spin coat it with resist. We're using a ZEP. The next step, we do the patterning with electron beam lithography. Electron beam lithography is not that fast. This process can be replaced with deep UV or in the future with nano imprinting, because the aspect ratio that we are doing is high. Nano imprinting still need more time to catch up. The next step is very critical. We use atomic layer deposition to deposit titanium dioxide film. The reason that we are using ALD is it will give us high quality with low material loss. But the problem is, or why other people haven't used it, is it will encapsulate your resist. It is not possible to lift off the resist because resist is buried under the titanium dioxide. So we keep depositing to encapsulate and stop with a flat surface. The next step is critical. So you will etch back to expose the resist and lift it off. So etching here does not define the structure, but just to expose the resist to have a high quality structure, which is a complementary of our resist with the same height. So some SEM of the representative of the structure. So on the top left, we can see top view of an SEM of a hologram. Top right, some of our structure is broken that you can see. The side wall is almost 90 degree. It's close to 89 degree. And more importantly, we can, in the left down, you can see we can put this structure very close to each other. This gap is around few nanometers. At the end of the day, we are designing digital mask, digital phase profile. In order to get a high quality and high performance component, you need to sample your phase as much as possible. You need to put this nanostructure as close as possible. So this fabrication process helps us. Giving this introduction and the fabrication, I will say how we design the lens. So lens is a phase plate. We need the phase from 0 to 2 pi. Here we show if we change the diameter from 100 nanometer to 220 at wavelengths of 532, if we have this building block which is titanium dioxide with circular pillar on top of glass, phase change from 0 to 2 pi. We use circular cross section to be polarization independent. So the blue curve is from FDTD Lumerical. The red curve is we want to see what is behind the phase accumulation. So what we did was we calculate the eigenmode value of the waveguide. We know the height of the waveguide. So the phase propagation through the height is 600 nanometer is 2 pi over lambda times effective index times propagation length, and as you can see is very close to the FDTD. In FDTD you capture everything. You capture the waveguiding mode, radiation mode, and all of the effect, the Fabry-Perot mode. But you can see these two curves are very close, which shows most of the phase is due to the propagation or the waveguiding effect. So our lenses still have a chromatic aberration, which means they do their best performance at their design wavelengths. So we designed 3 different lenses at 405, 532, and 660 nanometer. The figure on the right below, you can see each of these points correspond to a nanopillar with certain diameter for 3 different designs. So it's a complex value of the amplitude. The radius shows the transmitted light, which is here is more than 95% for most of the point, which means the transmission from this titanium dioxide nanopillar is very high. Potentially you can make high performance and high efficiency optical component, and most of them make a full circle, which means we can reach 2 pi phase coverage. We fabricate this lens with the fabrication process based on atom and layer deposition. This is top view SCM, zoom in top view SCM, and side view SCM of the fabricated lens. A portion of the lens, you can see the vertical sidewall and high quality titanium dioxide nanopillars. One of the important jobs that the lens do is it focuses the light. If you use this lens for imaging or for fabrication, the size of the focus potentially define the limit for resolution of imaging or resolution of the fabrication. So we designed 3 different lenses and we fabricate 3 different lenses with same numerical aperture of 0.85. So this figure shows the measured focal spot. Figure on the top shows the measured focal spot, cross section of the focal spot at 3 different wavelengths, 660, 532, and 405. The full wave max of which is limited by diffraction limit is mentioned in parentheses. Figure on the bottom shows the measure cut or horizontal cut through the focal spot. The full wave max of the measure is mentioned, is very close to what we are expecting from diffraction limit. So which means these lenses can focus the light down to diffraction limit. The other aspect or maybe most important job of a lens is how well they can do the imaging. So to test the imaging quality, we use the US Air Force target, which is an array of bar on an opaque screen. We shine the light with the 10 nanometer bandwidth and we make an image with metalens. So numerical aperture here is 0.8 and the lens is designed based on the geometric phase that I will get back to it at the end of my talk. So the smallest feature here are the bar with the width of 2.2 micrometer with the center to center distance of 4.4 micrometer. The same lens can resolve this smallest feature size all the way from the blue to the red. These lenses still have chromatic aberration, which means every time that we change the wavelengths, we need to adjust the distance between the lens and object to bring it to the focus. This is the reason behind the different magnification for different color. We also test another resolution chart, the figure on the bottom, which is Siemens star. So the minimum gap is 1.8 micrometer. This singlet 1 metasurface lens can resolve the smallest feature all the way from the blue to the red. We just want to push it slightly more to see what's the minimum resolution that we can get. We make our own custom resolution chart. It's an area of hole fabricated by focused ion beam on a gold-coated glass. So minimum gap here is 800 nanometer. You can see the lens still can resolve it, but you will start having a coma aberration. You can see the comet at the edge of the image. This becomes more visible if you reduce the gap to 450 nanometer, which is sub-wavelength gap. We still can resolve it, but the field of view reduce. So the reason behind it is we have a singlet, which means we have not correct for the chromatic and for the coma aberration and other type of aberration that reduce the field of view. To calculate this phase, you can just, it's a one to phase to require first to make a singlet, we use just one line equation. But if we want to design a doublet to get around the coma aberration or some other aberration to increase the field of view, one need to use other software like Zemax. So what the Zemax do is it will tell you or what's the best phase profile for 2-layer or 2 doublet to increase the field of view. If you want to increase the field of view, the other option is to do confocal macroscopy. That's what we have done here. So we have a lens and we scan it. We can get a diffraction limited here is 200 nanometer because we design an emergent lens over a large field of view. So that was about the single or wavelengths flat lenses. So the ideal is to increase the bandwidth of these lenses. That will bring more application so they can use it in the camera module or different kind of application. So for our lens, for the first part that I mentioned, if you change the diameter, you have a phase from 0 to 2 pi. Because the phase is limited at each point, if we need a phase, it translates to a nanopillar with certain diameter at design wavelengths. If we change the wavelengths, we do not have any control over the phase. We get what we already put it there. So if you want to design a chromatic lens, we need to break away from this constraint. One of the way to do it to expand the phase coverage. So here the lens is working the reflection mode. I'm talking about the figure on the right. The building block is a titanium dioxide nanopillar on top of a metallic mirror with an intermediate thin film layer of glass, silicon dioxide. So again, we do the FDTD simulation with the Lumerical. We change the width of this nanopillar. We record the phase for 2 different wavelengths. Here we can say phase is multiple of 2 pi. Why it is helping us, let's assume at some position at the lens unit the phase of 0.4. We can see we have several points that give us this phase at 500 nanometer wavelengths, but different phase and another wavelengths, 550 here. This immediately gives us a freedom to design a phase at one wavelength simultaneously with another wavelength. At least give us the freedom, then there will be an optimization process to make the whole library and make sure this still can be designed to make an achromatic lens. So we design a achromatic meta lens. You can see the simulation. It's a blue curve here. So we design it to be achromatic from the wavelengths from 490 to 550 nanometer, 60 nanometer bandwidth, close to an LED bandwidth. We fabricated using the same fabrication process that I mentioned earlier. we define a fractional focal length change, which is focal length of the maximum focal length minus minimum focal length over average focal length, and the value for the simulation is 1.2%. So the focal length doesn't change too much over the bandwidth. If you do not correct for it and I have a GML, geometrical base metal lens, so this fractional change is 16%. So we reduce it in the simulation more than 10 times. And in our experiment, we can see the lens have a fractional change less than 1.5%. So this is the red curve here. This shows the focal spot at the fixed distance from the lens, or the intensity profile of the lens from the fixed distance from the lens. You can see over this bandwidth, most of the light is in focus. So far I have shown we use mostly diffractive optics, and we calculate the phase for a specific configuration, for example, for different wavelength singlet, and we impart the phase using the nanostructure, and we calculate the available phase using FDTD. Now we want to see whether we can make a multifunctional optical component still having a one metasurface layer. So we are interested in the polarization. We want to resolve the circular polarization of the light. Let's first start. If we want to resolve circular polarization of the light using an off-the-shelf optical component, what do we need? So if the light comes and we want to make a polarized resolved imaging here, chiral imaging, we need a beam splitter, quarter wave plate, and linear polarizer to remove one of the helicity of the light. We need two lenses to make an image on a camera. So immediately you can see we need 8 optical components. Now the question is whether we can replace this with one metasurface layer. Here you are using geometric phase or Punch-Norton-Berry phase. So for impart the phase, now we need an building block. Here we use titanium dioxide nanofin. They act as an half-wave plate. If I have an half-wave plate and rotate it for circular polarization of the light, the phase imparted to it is twice the rotation angle. So we have 2 nanofin, blue one and the green one. The blue one focus the light for right circular polarization, and the green one focus the light for left circular polarization. So to design this nanofin, what you can do is you can use them, for example, for our case, we use FDTD from the Lumerical, and make sure if we have a left circular polarization input light, at the output it will convert it to the left circular polarization. More conversion means more efficiency in the design and device that you are making. So we design a point-to-point imaging system. So if I have a point, because we especially multiplex the lens, the blue one focus the right circular polarization on the bottom, and the green nanofin focus the left circular polarization on the top. To calculate the phase, we did an approximation of not considering the effect of the substrate, because the ray tracing, if you want to do it by MATLAB or just do it by yourself, it will become complicated. But if you want to have a better result, what you can do is you can use a Zemax. It will calculate the required phase profile by considering the substrate thickness to focus the light from a diffraction limit point of view. So we fabricate this using atomic layer deposition of the titanium dioxide. So to test these lenses, we use a facet of optical fiber. We put the fiber here. We put a linear polarizer plus a quarter wave plate to be able to control the polarization of the incident light. So we launch this fiber with a tunable laser with 550 nanometer center band wavelengths and bandwidths of 100 nanometers. So first we set the polarization to the linear polarization. Linear polarization can be seen as a equally left and right circular polarization. That way this lens make a 2 identical image with the same field of view of camera. We design the lens off axis, so which means it will not only focus the light, but it disperses the light as well. You can see it as a lens plus a grating. That's why this lens focuses the green light and disperse blue and the red. You can get the wavelength information at the same time. If you switch to left circular polarization, the figure on the middle, what it does is, so because there is no right circular polarization reaching the lens, image on the right disappear and image on the left enhance intensity. If you go to the right circular polarization, opposite effect is observed. We also did an imaging on a chiral object. So here we have an chiral beetle. So what the skeleton of this beetle is developed over the evolution is it will reflect left circular polarization and absorb right circular polarization. That's why if we have this beetle, oval lens, and LED for illumination, this lens make two images with the same field of view of camera. Image on the left is metallic because beetle itself reflects left circular polarization. Image on the right is dark because there is not that much of the right circular polarization reaching the lens. So to summarize, so we use ultra thin layer of the nanostructure, so 600 nanometer, less than 600 nanometer, to make a metasurface lens with high numerical aperture. I have shown they can focus the light down to diffraction limit. They are sub-wavelengths. They can resolve sub-wavelengths image, and also show how can we use or how can we break away from the diffractive optics to design achromatic lenses. And at the end, I have shown how can we use this concept to make multifunctional metasurface lenses to resolve the chirality without adding any complexity to the fabrication. Before I finish, I would like to acknowledge and thank my group member that has a significant contribution to this work, funding, collaborator, and the fabrication facility at Harvard. Thank you very much for your attention. If you have any question, I would be more than happy to answer.
Thank you very much, Reza. We really appreciate you taking the time to work with us. So in just a moment, I will hand this back over to Amy, Akil, and Reza to answer all your questions. But there are a few things that I'd like to cover first. If any of you listening and viewing now are interested in learning more about Zemax and Lumerical's products, please check out the websites that you see on the screen here. Note that we'll also be posting the PowerPoint for this presentation, so you'll be able to click on the links there. This webinar is part 2 of the 2-part series collaboration between Lumerical and Zemax. And in the first webinar, we gave you an overview of the different file types that you could use to transfer data back and forth between these software packages. So in just a moment, you'll see a poll pop up on your screen, and we'd really appreciate it if you could take the time to respond. Amy and Akil discussed the use of ZBF files, which are the first option shown in the poll here. And these files contain the amplitude and phase profile from the near-field simulation from Lumerical software. This file can be opened in OpticStudio, and then the resulting beam can be propagated through the macroscopic optical system using OpticStudio's physical optics propagation. And so then the next file type on the poll list here is the grid phase file. And like the ZBF file in the previous option, the grid phase files contain the phase distribution, which comes from Lumerical software, but it doesn't contain any information about the near field intensity. So this means that the incident beam profile would be defined inside of OpticStudio. But the grid phase surface changes the phase of the beam, just like a thin lens, and then OpticStudio can trace the resulting rays through the rest of the macroscopic system. And then, just since we didn't talk about it here, also the third bullet is for ray set file types, and these data files are used in non-sequential ray tracing in OpticStudio. These data files will come from a Lumerical simulation, and it contains the starting ray position, orientation, wavelength, and phase. So this is an excellent option for complex or highly engineered sources. Moving down the list, the fourth bullet point here, Lumerical can also generate BSDF files for use in OpticStudio, and these are for simulating scattering profiles. So Lumerical software can simulate the micro and nanoscopic interactions of light with a rough surface, and then that is used to generate a BSDF file, which OpticStudio then uses for the macroscopic ray tracing through the rest of the system. Okay, and then the last bullet point shown here for the poll is talking about the fact that Lumerical can be used to characterize gratings and to calculate the phase and amplitude or intensity for each of the diffraction orders. So then this information can be fed into OpticStudio just like as described in the preceding bullet points. So when this poll does pop up, we'd really appreciate it if you could select the file type that is of most interest to you.
Hi, so the first question is, are the transmission losses are constant for different diameter of the structures? So when we run the simulation, if the transmission is not high enough, by high enough I mean more than 90%, we just discard that option. But mostly I would say 95% of the diameter, the transmission is quite high. Again, Reza, so the next question is the distance of the column vary or only the width? So we fix the distance of between the two nanostructure, and that distance is based on the Nyquist theorem. If you want to bend the light to a certain angle, so if you define that angle as a numerical aperture, which is numerical aperture sine of that angle, we need to sample it at least lambda over 2 NA. Lambda is the wavelength, NA is sine theta. So that will tell us what's the maximum distance between the nanostructure is, and we would like to have distance smaller than this to make sure the efficiency would be high. So the next question is, what is the function of the SiO2 and metallic layer in achromatic lens compared to the first case that we showed? So for achromatic lens, we mostly excite the guided mode resonance. So, and we are working on reflection mode. So the metallic is mostly to reflect light back, so we get more intensity and we get more transmission. And the silicon dioxide is to enhance the guided mode resonance and slightly detach the mode from the metallic mode, because when you have a guided mode resonance, you have a transverse mode. You want to enhance it, at the same time you want to reduce the loss, so it will bring this transverse mode slightly away from the metallic mirror. So then the follow-up question is, did the metallic layer limit the transmission of the lens? Yes, it does, because you have a metallic, when you have a transverse mode, it will excite some kind of plasmonic mode there, and it will absorb the light. So if the best way is to replace it with the dielectric mirror. The second question is, or the next question is in the multispectral chiral lens, is the transmitted light purely circular polarized, or does it transmitted the elliptical polarization different from the pure circular polarization? In other words, is there any conversion or polarization that goes through the lens? Yes, it does. So the lens or the phase is based on geometric phase, which means if we want to have the maximum efficiency, you need to design a wave plate. So you convert the helicity of the light. If I have a left circular polarization, ideally after passing through the nanofin, you have an opposite helicity. And the phase is how much we rotate this half wave plate. So the next question is there work being done in increasing the achromatic range of the metalens? Yes. So we have a design that increase this bandwidth to more than 100 nanometers in visible range, but we still haven't published that result, but it is possible to do that. So the next question is the copper and plasmonic, can we use copper and plasmonic with your structure? It does, but we want to avoid from metallic structure because of the loss. So one of the most important factor that we try to promote here is we can increase the efficiency. The moment that you use a metallic, the loss come into the picture and you will lose the efficiency. And the next question, or the follow-up question, is it possible with TiO2? Yes, it is possible to do more bandwidth achromatic lens with TiO2. The next question is, what's the bandwidth of the multispectral chiral lens? It depends on the numerical aperture. If the numerical aperture here is very low, so I would say the bandwidth is within the 10 to 20 nanometers. If you go to high numerical aperture, or you can resolve the smallest feature size, the bandwidth reduced to few nanometers. So the next question is quite general. How long does it take to design a lens? And how long does it take to design and fabricate and just put everything together? If my supervisor asked, I would say 2 weeks. But to give an honest answer, so if you want to design this to building the library, it might take, depend on the, a best estimate of the height, it takes few hours, obviously depend on your machine. So you build the library within the few hours. If your phase is quite challenging to calculate using Zemax, if you're expert, within 1 or 2 hours, and they're running the simulation in FDTD takes between 8 hours to 24 hours. I would say if you start from beginning to the end, it should take 2 days. The second question is, have you done a green lens with imperfection and radial index of refraction? So I'm not sure. We didn't have any green lens, but what we have is, based on the phase library that we have, we can impart any different phase. And the green lens is based on the gradient index through the propagation, and we don't have any gradient index through the propagation. So the next question is, how robust are the metalenses to angle variation with respect to the source of the imaging object? If we have a singlet lens, and they are quite sensitive. Let's say if you have a numerical aperture of 0.85, within the 1 or 2 degree, you will lose the resolution of the imaging. But obviously, you can increase this field of view or tolerance the incident angle by designing a doublet or triplet. So the second question also is about the field of view, bandwidth, and limitation of these lenses. So we just shows the singlet, very sensitive to the angle of incident, or if you define it in an imaging, you can call it as an coma aberration. It's very sensitive. The bandwidth, and it can be improved by designing a doublet.
Hi everyone, this is Amy here. I'm just, I think Dr. Khorasaninejad has to leave in about 5 minutes here. So if you have any more questions for him, please feel free to type them in the questions panel. Myself and Akil will be around for a bit longer, so we'll come to the more Zemax and Lumericals or general questions in a bit. But I just wanted to make sure we could address more of the questions for Reza first. So if you have any more questions for him, please feel free to type in the questions panel, and we will stick around a bit longer to answer the numerical and Zemax questions. Yeah, Akil and I can start answering the numerical and Zemax questions. So we have one on for the full metal lens simulation. It should have a reasonable amount of scatter into angles that are far from the propagation axis, and how can we account for this? So on the numerical side, so the FDTD simulations, all of this is taken into account when you take the near field results. That include all the scattering to all the possible angles. But I'll let Akil comment on how this is handled on the OpticStudio side.
Great, thanks, Amy. So yeah, in OpticStudio, when you have your ZBF, it really depends on how extreme your scatter angles are. If they're not that extreme, they should be fine in the ZBF file. If you do have very extreme angles, then you're going to need to use the grid phase file, which only accounts for phase and doesn't account for the amplitude or the rest of the electric field. And it's only array-based model when you're using the grid phase. Yeah, so that right now high angles are a limitation for ZBF currently.
Yeah, for question for the FDTD simulations, for the design of flat lens was done using plane wave. So how does one design for incoherent light source like lamps and LEDs? So if you were trying to do this in FDTD solutions, because we solve Maxwell's equations, everything is always coherent, but there are ways to incorporate incoherence into the system. So if you're looking at spatial incoherence, like or temporal incoherence, like in the case of an OLED or LED source, what you would do is you would simulate three dipole sources with orthogonal orientation. So if you have a dipole oriented at X, Y, and Z orientations, and then you can add up the results incoherently, and that's going to give you basically a true incoherent light source. And if you have polarization coherence, you can also, if you have a plane wave, you can also do two plane wave simulations with orthogonal polarizations and add the results incoherently, and that'll give you an unpolarized or incoherent source as well. I know that's a pretty brief explanation, but I will post in shortly just a link that talks a lot about how to do this. And this is certainly something that we do all the time in FDTD solutions. And a follow-up question on that is what happens if you have a oblique instant of plane wave source. So again, like in FDTD, you can angle the plane wave however you want. In any angle, especially if you're looking at those initial pure simulation of the unit cells. I did fix it at normal instance, but you can freely change the angle of instance.
Okay, so we have a question. What is the difference between Lumerical FDTD script, far field exact, and Zemax OpticStudio to find the far field focus of a microlens? So in OpticStudio, once you have your ZBF file imported, you can actually optimize for the small spot size, which should be your focal plane. And by doing that, you'll be able to find out what your exact far field focus is. And then Amy can talk about the Lumerical side.
Sure. So the far field exact function basically allows you to calculate the result, the field at any point in the far field in free space. So it's really only for free space propagation. So if you do just want to see where your light is focusing, if you do the lens simulation, you just want to see what the focal spot is in free space, you can do that with far field exact. And we have a lot of examples online that shows you how to do this. But what it doesn't allow you to do is propagate it through a lens system. And as you can see with a lot of what Reza was doing, it's not enough to just assume free space propagation. He needs to further optimize the lens system. So this is really where OpticStudio is ideal for that.
And so I see another question. How to model off-axis imaging? There's a sampling problem with off-axis high-order polynomial phase profiles, and how do you solve that sampling problem? So in OpticStudio, when you're using the physical optics propagation tool, at each surface, inside of the surface properties, you can actually resample, and you can either choose to let it automatically resample, or you can choose which sampling you want. And so this tends to be a process where you have to go back and forth and check the sampling, and then check your beam files, and keep changing them for each surface if you're having issues with them. We also have several knowledge base articles discussing how to sample correctly. So feel free to look at the knowledge base if you're more interested in how to sample in physical optics propagation.
Yeah, and I'm just pasting to everyone here. There's a link to our knowledge base on how to simulate sort of incoherence. So that includes sort of spatial incoherence, polarization incoherence, and temporal incoherence in FDTD solutions. And I just have another question on how, can you explain how you build the 3D lens model in Lumerical? So yeah, it was actually really easy. I just have a script that reads off my desired phase profile and then reads off the sort of the duty cycle map, and then it positions it basically figures out what the duty cycle is. And we will be putting that example online shortly, so you can use the scripts. I'll share the scripts that I use, and you can download that. But I'm just pasting here in this chat window here. There's a very similar example, a slightly different application. This is for designing a binary phase grading mask. So it's not for a lens design, but it's more of a sort of a lithography process. But the idea is exactly the same. They also define some target intensity, and then they figure out where to position these, what the duty cycle to set is for these lens. And there's a scripts in that link. You can find scripts for 2D and 3D and how to construct these lens. And I basically use the same script for that, even though it's for a completely different application. So you can start with that, but we will hopefully be putting these examples online shortly.
All right, thank you very much, Amy and Akil. It looks like we have answered all of the questions, and big thank you to Reza, although he did have to leave the webinar, so he's not here now. If we didn't get to any of your questions, we will follow up with you via email. So thank you all for attending and for participating, and have a great rest of your day.